Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Hello everyone, welcome to this lecture, and today we will look at the influence of overload on the fatigue crack growth. In the last class we looked at the different crack closure mechanisms, starting from plasticity induced crack closure or plastic zone size induced crack closure, and then followed by the oxide induced crack closure, the roughness induced crack closure. The second phase particles act as a wedge between these two crack surfaces, which we have identified that during mode 2 kind of a failure, how the wedging takes place and how the crack growth is retarded or crack closure is facilitated and so on. And one of the important idea which we were discussing yesterday is the plastic zone size developed ahead of the crack tip affects significantly the crack growth rate. That is something which we are trying to understand. So today we will try to study that aspect, that is the influence of overload on the crack growth. And what you are seeing here is in this plot is crack length versus number of kilocycles. And this is a normal fatigue cycles with the amplitude shown here, the maximum and minimum load, and this is shown in the crack length A. And what is shown here in the B is yes, a fatigue cycle is done with this amplitude, and suddenly the amplitude is increased in the positive and negative direction, and then it back to the normal cycle. So this kind of overload also seem to have retardation, small retardation we are able to witness because of this overloading. And what is shown in this the third curve is only the amplitude of the positive load is increased significantly, and there is no second, the negative side load, that no compressions, only in the tension side. So that creates a significant retardation of the crack growth. That is the tensile overload points. You can see that. Okay, so this is fully refers to overload points. The previous case, the tensile overload points significantly retards the crack growth. Overloads in general retard crack growth rate. A tensile overload is very effective in retardation. So this is something which you are seeing. So what Wheeler has observed is this. It's a Wheeler model. In view of overload, the plastic zone size is much larger. So this is what's shown in this schematic animation. The original crack length is A, and then you can see that this plastic zone size is small. So the incremental crack growth will take place within this small plastic zone region, and that is after the regular amplitude cycle here. Once the amplitude of the cycle is increased at the end of this overload cycle, then you can see that increase in the plastic zone size ahead of the crack tip. And then what happens is this crack has to now go through the larger plastic zone region, and which will be retarded. So that is the basic physics behind the retardation. Okay, so that you can also see that the residual stress developed ahead of this crack tip also significantly higher as compared to the previous case. So that is what is shown here. So we will complete this animation now. So small plastic zone size is now a bigger plastic zone size, and now we will see how it changes to, it is subsequently, you can see it has gone back to its original plastic zone size, but which is interestingly within the larger plastic zone size. So that is what it is. Okay. So the crack retardation force will be much small in the small plastic zone size. That is an idea. So subsequent crack growth is retarded due to this, and to account for this, Paris law is modified as dA by dN is equal to psi r times C into delta k to the power m, where psi r is equal to delta A plus, I will zoom in, delta A plus R PC. This is a typographic error. This is plastic zone size RP per cycle, PC divided by RP naught, that is plastic zone size of the overload. So which is overload P naught. P naught should be here. So this factor will be less than 1. So the crack growth rate is retarded. So that is how we should read this equation. So gamma is adjustable calibration factor, which is less than between 0 to 2, and when gamma is equal to 0, then it becomes a Paris law. So what you are seeing here is, again, at the end of the overload, the plastic zone size is much bigger, and at the end of the normal cycle amplitude, this is much smaller. So now we will turn our attention to the environmental effects on the fatigue crack growth rate curve, and this is dA by dN versus delta K, and what you are seeing is the reduction or elimination of the delta K threshold and an overall enhancement of the crack growth rates. So what you are seeing here is this point is delta K threshold. It has been shifted to the origin. That means there is no delta K threshold exists. It is the aggressive environment has eliminated the threshold. That means the crack will start growing instantaneously as compared to the normal environment. That is how we should look at it. And this is for the one situation. And the typical for the fatigue in the liquid environments, and that causes the stress corrosion. So this is also a characteristic of the liquid environment and the stress corrosion. And there is another situation also. You can see that it is not just delta K threshold is 0, and also you can see the sudden increase in the fatigue crack growth rate. Rate is also significantly amplified, and then you can see that effect here also. At intermediate delta K level, note the enhancement of the crack growth rates. That is, this is what is shown here. So this is a normal environment and then aggressive environment. So these are all very important effect of environment on the fatigue crack growth rates. So what you are seeing is another very typical crack growth rate increases like this, and this could be because of one of the environmental effects such as gaseous hydrogen. The environment could be gaseous hydrogen, and there is overall enhancement of the crack growth rates except near the threshold, and delta K threshold can be higher in the corrosive environment, and the corrosion product increase the volume of the material contributing to the crack closure, that pushing up the delta K. So you can see that sometimes the corrosion products also helps in pushing up the delta K. Here it is a beneficial effect by the corrosion products at the crack tip. So this kind of positive action also sometimes visualized. So now look at some of the primary issues in fatigue crack growth calculations. In general, structure over its lifetime experiences a variable amplitude loading. One of the most challenging tasks in practical problem is to establish a load spectrum acting on the structure, and the procedures for evaluating the crack growth in a constant amplitude and small scale yield conditions are fairly well established. However, evaluating the geometric factor as the crack grows, modeling of the crack closure, effect of overloads, influence of environmental conditions pose a challenge even in the case of constant amplitude loading. So these are all some of the issues with the fatigue crack growth. And so another issue is under the variable amplitude loading, similitude conditions may not be valid. And a simplistic model, if the similitude conditions are assumed, can be written as if this is some modification for different situations. So it becomes like a cumulative effect. So some model has been developed, and we will not get into the details, just to give you a idea of what happens in a different kind of situations, how the fatigue crack growth are calculated. Just I want to give the perspective idea. And if you look at the summary of all the empirical fatigue growth models, is tabulated here. I have just flashed it at the beginning also. Just keep it as a summary. We will stop it here. And this is for the crack closure models, where K effective has been incorporated into this Paris law equation. And this is proposed by Elber, this is proposed by Wheeler, and then for a variable amplitude loading. And there is a large plastic zone, and instead of delta K, delta J has been introduced, which is which we will discuss in the next few slides. J integral. Okay, we will now turn our attention to the J integral. One last fracture toughness parameters in the table. And before we get into the J integral, there we need to know something about path independent integrals. And SLB introduced a number of contour integrals. And what is contour integral? It is schematically shown in here. This is a contour, basically a symbol of a line integral. Then so what you are seeing here is integral w dy minus tin dou u I by dou x into ds is equal to 0. So what the parameter what we are seeing here is we have already seen in the theory of elasticity, but they have been recasted in a different form. So that we have to understand first. So W dy is nothing but the strain energy per unit volume, and dou u I by dou x is work done. So strain energy minus the work done is normally considered as a potential energy in theory of elasticity, and the rate of change of potential energy with respect to crack length, incremental crack length, is something related to our strain energy release rate, something of that kind. So that idea has been simplified after several modification in a simple equation like this. So in a nutshell, if you look at the idea is something related to the strain energy release rate. Okay, so that is what we have to appreciate this equation. And W can be written as integral sigma ij into d epsilon ij, and Tn is represented as tau ij and n. This is a Cauchy formula. This also we have seen already. And it is appropriate to use the symbol U for the strain energy instead of W. Okay. So this is a contour, as I just mentioned in the beginning, the line contour, and this is a outward normal, and this is a traction vector. It's a traction vector Tn. So we will see now. And the traction vector here is written in the indical notation. So it can be expanded to x, y, and so on. So that's how it is. We will see how it is written. For linear elastic solids, the strain energy per unit volume is written like this. This equation we have already seen, and this is the whole expression for the linear elastic solids. What we have to understand is the J integral is used in LEFM, and J integral is also used in the nonlinear fracture mechanics, and J integral is also used in elastoplastic fracture mechanics. So that's how we have to see how it is being used. Okay. So what is J integral? So what you are seeing here is a crack. The important point to note here is the crack is not loaded. So the contour one goes like this, the other contour comes in the opposite direction, and then it is a closed contour. Okay, what you have to appreciate is it is closed contour. A, B, C, D, E, F. It get closed here, and then it starts with one face of the crack, and then it ends with the other face of the crack, and the crack is not loaded. So in between it is a free surface that you all know. So this is consider the closed contour A, B, C, D, E, F, A, and from Eshelby's results, the integral, this line 1, okay, this that line contour 1 plus integral CD, this face, and plus line integral 2 plus FA is equal to 0. So the total, value of this integral system is supposed to be 0. That is the Eshelby's assumption. Integral CD is equal to 0, integral FA is equal to 0 because the traction in the cracked surface is 0 because it is a free surface. So when you substitute this, and then the traction y is equal to 0 and dy is equal to 0 on the cracked surfaces, so you get the interrelationship between line integral 1 and 2, and this is written like this. The negative sign indicates that the direction of the line contour is different. So yeah, this goes like this, this goes like this. This result implies that in crack problems, if a contour starts from one crack face and ends in another crack face, the magnitude of the line integral does not change. The result also indicates that J integral is path independent. So let us summarize the basic assumptions or features of J integral. So there is a crack in the body, and then the contour is drawn from one face to the other face of the body. Take a line integral path that encloses the crack tip such that the initial and end points lie on the two crack surfaces. The J integral is defined as integral W dy minus T I n into dou u I by dou x ds, where W represents the strain energy per unit volume. It is appropriate to use a symbol U for a strain energy. So we can rewrite this expressions like integral into u dy minus T I n dou u I by dou x into ds. We can rewrite like this. And what we can Now look at this. U we can write like this: integral sigma ij into d epsilon ij. U is a strain energy, and it is a point function. It varies from point to point within the body of the component. The second term of J in an expanded form, integral tau, integral Txn dou ux by dou x plus Tyn dou uy by dou x into ds. Tn is the stress vector, which can be obtained by Cauchy's formula, like we mentioned it before. So this thus we know already, and we can just verify this J integral for a double cantilever beam specimen of this kind. So what is shown here is the same contour is drawn in this. So what we have to appreciate here is all these surfaces are free surfaces. So we will see how it is useful. Since J is a path independent, choose a path for which the line integral can be evaluated conveniently. Consider a path which starts from one crack face to the other face through a boundary of the specimen. For clarity, the path is shown slightly inside the boundary as a clean line. So as such, you can choose this as a boundary, and they are all free surface. So how do we write the equations for this? Surfaces CD, DE, EF are free surfaces, hence the attraction is 0. Thus the second term is 0. So this one is 0. U is also negligible, hence no contribution to J from this side. Okay, that's what it is. And what is remaining? On BC and FH, U is negligible. This is because energy is only due to shear and the contribution is negligible. And if you look at this other point is only this two phases. So we have to write it like for this two phases, which is written like this: minus 2 integral 0 to h this height into Ty dou u by dou x ds. And this particular double cantilever beam problem, the strength of materials gives the a solution as the slope of the beam. This from the strength of material solution you can directly take it, and which is given like this. So the what we have to integrate, evaluate is only 0 to h integration 0 to h into Ty by ds, Ty into ds, which is nothing but P by B. This is the value of this integral, so you can write it like this. So what we find out as a J is also equal to G in the fully elastic material. For elastic material, J is nothing but a strain energy release rate. Okay, but how we can apply to the nonlinear problem or elastoplastic problem that is what we are going to see now. So in elastoplastic material behavior, what is the issue? So if you look at the stress strain diagram, up to yield point, or as long as it is linear elastic, it can come back. If you remove the load, you can trace the path. Even in the non-linear elastic mode, if the load is removed, the path can be traced. The moment you cross the elastic limit, and if you go to the plastic limit, then they trace the unloading path is different. Suppose if you take this particular line for a given strain, there could be two stress values. For this particular strain value, you have two stress values. So this is the complication in the elastoplastic deformation. That's what is shown here. In elastoplastic loading and unloading paths are different. For one strain value, two stress values are obtained. Need to keep the track of loading history. That is going to be a challenge. That is why this elastoplastic is complicated. So we will see some of the intricacies in experimental determination of J. Elastoplastic behavior of material makes the analysis fracture mechanics complex. Unloading of material occurs when the crack is allowed to grow. A designer is interested only on the condition of onset of the crack growth, which means crack has still not grown but has reached a threshold that any small increase in the load would result in crack growth. If crack growth is not allowed, unloading does not take place, and elastic plastic material behavior is same as non-linear elastic behavior. So this is some of the important points to be noted as far as determining the J. While performing the experiment, unless a crack is allowed to grow by small distance, one would not know whether the threshold point is reached. When the growth of the crack is allowed in experiment, unloading occurs and the J integral is not rigorous anymore. Since better techniques are not available, allowing a small crack growth in J experiment is a compromise from an engineering point of view accepted widely. Unloading during small crack growth does not change significantly the value of J measured experimentally. So these are all some of the points to be noted. And then we now look at the graphical interpretation of J for the linear elastic solid, the load versus displacement curve. So as we just mentioned, as far as the elastic solid is concerned, the J is equal to G, the energy release rate. For the nonlinear elastic solid also, it is J is the area within this enclosed region. J can be defined as J is equal to minus integral 0 to delta into dou P by dou A at delta into d delta. So this is the definition of J, and we can just look at the simple experiments. A single specimen approach, where you can see that being the uncracked ligament is about 50% of the W. For J experiments, the specimen is considerably thin. Large plastic zone is recommended for J experiment in contrast to very small plastic zone for K experiment. When the specimen is loaded, it deforms as two rigid bars connected by a plastic hinge. So it is shown here like this. This is the plastic hinge. And plot P versus delta, and area under the curve is directly related to J. So that is how the J experiments are conducted. So we can just look at this graph schematic. P versus delta. This is for J for a bent specimen. So this is the area under this curve, which is related to 2A divided by B into B. B is the thickness of the specimen, and other dimensions are given here. A is area, B is this distance, the plastic zone distance. So J is a stress intensity parameter, and Hutchinson, Rice and Rosengren independently showed that J characterizes crack-tip condition in a nonlinear elastic material. They showed that in order to remain path independent, stress strain must vary as 1 by R near the crack tip. It is given like this, where K1 is a proportionality constant, N is the strain hardening exponent. For a linear elastic material, N is equal to 1, and one gets a 1 by square root or singularity in such cases. Okay. So I just would like to stop here. What we have realized is J is also a stress intensity parameter for the completely elastoplastic material, and it has been shown that it is very useful parameter, even though it does not, even though it produces a significant plasticity at the crack tip, and even for the small crack growth is a compromise in the J experiment, but nevertheless the experimental results are useful. That is what people have reported in the literature. So I will stop here, and my intention is just to give you, what is J integral and how it is being characterized and how it is compared with the other fracture parameters. Okay. And beyond that, I don't want to discuss in this course because it's not in the scope of this syllabus. And I urge all our students who are interested in getting more uh, information about the other parameters or details about this experiments, please refer the other course by Professor K. Ramesh of Applied Mechanics, the course on fracture mechanics. I recommend you to follow that. Okay. We will stop the discussion here, and then we will now continue with the next lecture. Thank you.